In case you don't know me, I'm Richard Jaenicke. I'm with Green Hills Software. Yes, this is different than the last time I was here. I'm coming to you from a software perspective. In fact, when I called up Jerry and said, hey, Jerry, can I sponsor, be one of the sponsors here for ETT? He said, Rich, you do realize you're working for a software company, don't you? and I was just thinking, well, it is in the company name, so I did have a hint before I joined that it was software. But today I'm going to be the one presenter that tries to bring you a software perspective. And this is the software perspective on multi-core processors being used for safety-critical applications. And here, the real key is determinism. Just like most real-time systems, we really need very strict determinism, even more so in avionics. And that's where I'm going to focus. But what's the big deal? Because multi-core is everywhere. It's been here for a long time. It's in highly regulated industries from medical imaging to casino gaming to financial trading. It's even flying in the non-avionics portions of airplanes. So what's the big deal? Why isn't it in safety-critical applications? Well, for avionics, it's really all about determinism and to some point being really conservative on the certification authorities' standpoint. I'm not really sure how to ensure strict determinism, enough determinism to make sure that that if you have a display, a cockpit display, that you can still see the elevation and the altitude, and that they're being updated on a regular basis, on a timely basis, so you're seeing good information. Or even now, you're pulling on the joystick, you're moving the joystick around, it's all electronic, there's software behind it telling where the ailerons to go. You want that to kind of work in a very timely manner, and if that gets stuck, something bad can happen. Now, there's different levels of safety critical. Their design assurance levels range from E, which is no real safety effect, to A, which can create catastrophic events. And up at that highest level, at DAL-A, the failure rate on the hardware side is such that you're not really allowed to have a failure at the system level, except for once every 114,000 years. Now, we know we aren't going to have any planes that are flying that long. So it pretty much means, you can't have any failures at the system level. You can have failures at lower levels, but they get caught. You have redundant systems, you have other systems that are monitoring and substitute something out, but at the top level, you don't have that failure. And because we know what happens when something like that doesn't actually work. We had faulty sensors, or really the main, or the initial part of the cascading failure in the Lion Air crash. We don't know the whole story behind the rest of it. What we do know is that these systems are really complex, and it makes these evaluations and these mitigations very difficult. And that's where multi-core adds on top of that complexity. So let's start with how you handle achieving the determinism for a safety-critical application if you only have a single core working. Either you have a single core processor or you only use a single core out of a multi-core processor. Well, you do that by partitioning the applications in space and time. You want to make sure that if any one application goes rogue, that it doesn't adversely affect or critically affect the operation of another application. So you do that by partitioning the memory space. That's easy because you have hardware support for that in the memory management unit. And then you partition in time as well. So this has given each application a time slot to execute in. And when its time slot's up, even if it's not done, you move on to the next one. You assign the time frame or the amount of time in that slot by what you calculate to be the worst case execution time. And if it takes longer than that, then something's probably wrong and you wanted to shut it off anyhow. But you shut it off and you move on to the next thing. And that way you ensure that these applications are executing independently. So it's a little bit more complex when you get to multicore because now you have applications executing concurrently on the ones on different cores, and they can bump into each other more, particularly when they're vying for the same shared resources. And multi-core processors have lots of shared resources, whether it's shared cache, shared memory, or I/O or accelerators. Every time two cores are trying to access the same resource, one of them doesn't get it. And that causes its execution to take longer. And it's a little bit in an unpredictable manner, the way that modern processors work. There is finally some guidance from the safety certification authorities on how to deal with this, or at least at what level you need to deal with it. And that's in the form of a position paper called CAS 32A. And we'll come back to that later. So if you have this contention, you have this interference, one thing you can do is try, well, instead of fixing it, why don't we just avoid it? Can't we just avoid it? You know, I guess one approach that I've seen one company take is you just pretend it doesn't exist. That one I know doesn't work very well, because this is real, and I'll show you some examples. Another approach is to say, well, hey, instead of having all these cores trying to go after the I/O, why don't I take all the applications that do I/O and stick them all on the same core? That way you don't have multiple cores trying to access the I/O at once. And if you don't have very many I/O applications, that could work. You know, usually there's more I/O than that, so that core 0 gets loaded up and the other cores aren't used that much, so you have poor utilization. But once you get beyond I/O, it's a little harder. You know, what about the memory controller? There aren't too many applications that don't need access to memory. So you're going to have contention there, unless you put all the applications on one core, in which course you might as well not have a multi-core processor. And memory access really is the biggest culprit. Let's pretend what you really want to happen is to have your highest criticality application running at DAL-A get most of the memory bandwidth, in this case 80%. And another application, a medium critical application running at DAL-C, get 20% of the bandwidth. Okay, that's what you'd like. Now, unless you enforce it, it's just a hope or a dream. And what you think you might get is that you split that up. You know, like they both are trying to access memory, one will get it half the time, one will get the other half of the time. But that's not always the case. There are worst cases where it actually flips. If the lower priority, lower criticality application is actually doing a series of writes, it's a memory hog and it's doing writes. You guys are hardware people, most of you, and you know that the writes pipeline, so they get in there and they block out the reads, and you can actually have your highest priority application be blocked out and get only 10% instead of the 80% you were hoping for. And this isn't just theory. This comes from actual measurements done on a quad-core PowerPC. So what is the general solution to this? Well, it's really trying to you need to implement some level of quality of service. And it turns out that all these shared resources are accessed through the on-chip interconnect. So the interconnect is a focal point, and you can try and implement the quality of service there, either right in the interconnect itself, or what's a little easier is the processor's interface to that interconnect, or the processor core's interface to the interconnect. And you can say, okay, I want a certain amount of bandwidth to that interconnect being allocated to each core. In this case, core 0, you say I want 60% there and 15% on the other cores except for core 3, where he only gets 10 because he's not very important. And you set that threshold on a time window. So if core 1 or core 2 sits there and tries to grab too much of the shared memory, well, it hits its threshold and then it has a timeout until your time window resets. And that can be very disruptive unless those time windows are very small. So the smaller the granularity on these time windows, the more smooth the operation will look from the outside overall. So that's really what you need to do. Green Hills does this in something it calls bandwidth allocation and monitoring, or BAM. And we haven't seen really any other good solution or any proposals for good solutions on how to deal with this. So let me back up for a minute beyond, how do you solve interference to how do you solve the safety problem overall? Well, as part of these certification efforts, there's lots of different parts, layers that go into this. There's all the planning documents, analysis, there's traceability of requirements, back and forth, there's design reviews, you do tons and tons of testing, and you do structural coverage testing. All of these are each trying to find faults so that if a fault makes it through one part of the process, that you can catch it on another part. Let me focus on the traceability for a second. So you start with high-level requirements for your aircraft, for your avionics, and you break that down into lower-level requirements, and then each low-level requirement has some source code that implements that requirement. The traceability comes back and says, well, not only do you have source code for a low-level requirement, but each and every line of source code has to be there for a specific reason. It has to be there to meet a specific low-level requirement. We don't want extra lines there, extra source that we don't know what it's going to do. And then every low-level requirement has to be there because it's helping to fulfill a high-level requirement. And then you get to the testing part, where you have test code that tests that each one of these requirements is actually met. And once you get into the multi-core realm, the number of variations and combinations really explodes. And for DAL-A, the highest level of criticality in multi-core just requires a huge amount of testing. So on this slide, at the top is the number of lines of source code in Green Hills Integrity 178 RTOS, safety certified RTOS. You can see that when we moved from single core to multi-core, there wasn't a big increase, although note that this is a logarithmic scale. That's because it was already architected to do not only time and space partitioning, but resource partitioning. So handling multiple cores and shared memory were just more resources that already fit into the design. But the testing that was required went up exponentially. There's 250 times more lines of code for the test suite than there are for the kernel itself, for the RTOS. And in case that doesn't look big, and you're not used to looking at logarithmic scales, here's what it is on a linear scale. You can see that, heck, the RTOS itself is infinitesimal compared to the numbers of lines of test code. This is a huge amount of work. It's many, many man-years worth of work. It takes special knowledge of the processor architecture in order to design it, but really to test all the corner cases. And it's something you don't want to have to do. You don't want your customers to have to do it. You want to it's really incumbent upon us as COTS vendors to provide this level of quality product and testing and certification support such that the end customer can actually achieve the certification. So that's really my takeaway to you guys. There's some things here that we can't leave to our customer. Many companies say, oh, that really is a system level issue. But there's things like handling interference inside of a piece of hardware, inside a piece of a multi-processor core that you can't do from the application level. You have to do it down at the hardware level, at the OS level. You have to provide all of these testing. It's too expensive to try and do it, fix it after the fact. And that's really the way that Green Hills approaches this, is that we have to do our job to every little bit that we possibly can do just to make our customer's job even remotely approachably doable in a reasonable amount of time with a reasonable amount of risk.